Good evening. Welcome back to Mission Tackle the Problems. So, this is the fourth session of the new mission which we call as Mission Tackle the Problems. Today we will be dealing with a few problems in classical mechanics. Okay. So, we will see how we can solve a few problems. Also this along with this Mission Tackle the Problems, we were conducting this super solver competition, right, so that you can involve in it. Okay. So, during the live session, for a short period of time, there would be a Google link appearing, Google Docs link appearing in the comments. You can get in, join there and register for the competition, and you will get the question via email. So, those of you who have already taken part in the competition know about this, and the question will be sent to you. You can solve it and send it back to get attractive prizes from Unify Physics. So, let us go into Mission Tackle the Problems for classical mechanics. So, here is the first problem. All right. These are problems which we have selected from the previous NET JRF question papers. Okay. And this is the first problem. This was asked in the NET JRF exam in June 2011. So, here it is, the Lagrangian of a particle of charge E and mass m in an applied electric and magnetic field is given by L is equal to, so this is the Lagrangian. You might already know it from your textbook. This is a standard problem that we do for velocity dependent potentials. Okay. So, the Lagrangian for a particle, for a charged particle in an electromagnetic field, it is an example for a velocity dependent potential. This is the Lagrangian. Okay. And it is given where A and phi are the vector and scalar potentials corresponding to magnetic and electric fields respectively. Which of the following statements is correct? The canonically conjugate momentum of the particle is given by P is equal to mv vector. Okay. Is that right? We can easily check this, all right, because we know that canonically conjugate momentum, we usually write it as dou L by dou x dot, okay, Px, or simply P, right, it is dou L by dou x dot. Now, if you look at this Lagrangian, we can write this Lagrangian in this form. It is half m x dot square plus y dot square plus z dot square, right, plus E a dot v. So, a dot v will be a x x dot plus a y y dot plus a z z dot, right, where x dot y dot z dot are the components of the velocities along x, y and z axis respectively. Now, if you look at the x component of the conjugate moment, you take dou L by dou x dot. As usual, you get an mx dot from here, okay, but that is not all. That is not all. We have an extra term appearing from here, E a x. Right? This is just one component. So, if you write it, if you can also get py and pz. So, in total, right, in total, you can write the canonically conjugate momentum as p vector is equal to mv vector plus E a vector. Okay, that is the canonically conjugate momentum. So, it is not mv vector. Okay. So, that is the canonically conjugate momentum and not p equal to mv vector. Right. For velocity independent potential, it would be p equal to mv vector in some cases for a free particle, for example, but for a velocity dependent potential like this, it is p is equal to mv vector plus E a vector. Okay. All right. So, that is not the correct answer. We can exclude that from our options. Now, the Hamiltonian of the particle is given by h equal to p square by 2 m plus E by m a dot p plus E phi. Is that correct? We can easily check this. It is easy to check this. Okay. Let us do that here. All right. So, we will just check this. So, you have got L is equal to half m. I will write it like this, all right, summation I xi dot square plus E summation over I ai xi dot and minus E phi, all right. So, what does this mean? This summation over I xi dot square means, okay, by this summation over I xi dot square, what I mean is this, all right, this is equal to x1 dot square plus x2 dot square plus x3 dot square. Right. So, I have made use of a convenient notation whereby x1 stands for x and x2 stands for y and x3 stands for z, that's all. So it's basically x dot square plus y dot square plus z dot square. Okay. Now we can just look at, so we already know that the canonically conjugate momentum is given by mv vector plus e vector. We already saw, in order to exclude the first option, that p is given as mv plus ea. Okay. Now from here we get the velocity v is equal to p vector minus ea vector divided by m. Okay. Now we can find the Hamiltonian by this relation, h equal to summation over k p k q k dot minus L. This is the standard relation for the Hamiltonian of any system. Once you know the Lagrangian, this is known as a Legendre transformation. Right? You make a Legendre transformation to get the Hamiltonian. This is the Legendre transformation that you are making, which means that you need a function, okay, where all the qk dot will be written in terms of the momenta. Okay? We don't need velocities in the expression for Hamiltonian, so we will write it in terms of the momenta. Okay? All right. Now that would be the Hamiltonian. Now if you do this, all right, instead of qk, in this case you will have simply we'll write it as summation over k, okay, and m vk, all right, the kth component of momentum, plus eak, right, multiplied by vk. This is just the momentum, okay, the kth component of momentum, right. This is instead of qk dot we write it as vk, okay, minus half mv square minus ea dot v plus e phi. Okay. Now it's just a matter of substituting it back, and the final answer that you get, I don't want to spend too much time on calculating the details. You just do this, and wherever this v appears, you have to substitute in terms of pk. All right. So you have to use this expression. So this is very easy to simplify. In the end, you will get a result like this. Okay. H is equal to p minus ea square divided by 2m, okay, divided by m plus e phi. All right. It looks like that. Okay. So this would be the Hamiltonian. This would be the Hamiltonian. Okay. Now maybe there was a 2 here, I have to check. All right. So, but the thing is that it's not this. This is not the correct answer. It's not p square by 2m plus this thing. No, there's another term here. All right. Now this can be done by what's known as a minimal substitution. Okay. In minimal substitution, what we do is that wherever this p appears, you will take it as p, you will substitute it as p minus ea vector. All right. So this should appear in the expression for Hamiltonian. So this answer is also wrong. This answer is also wrong. So you don't, we know that this is not the correct answer. We already know it from our lectures. All right. Now here is another option. All right. L remains unchanged under gauge transformation of the potentials. All right. L remains unchanged under gauge transformation of the potential. What do we mean by gauge transformation? All right. Now this is a very important part for a net JRF exam. All right. What do we mean by a gauge transformation? What do we mean by a gauge transformation? Right? So when we talk about a gauge transformation, the easiest way to remember this is in terms of the 4 vector potential, what we call as the 4 vector potential. Okay, 4 vector potential. Right. So here we will be using again, so for the convenience we will take c equal to 1 where speed of light is equal to 1. Okay. So in terms of the 4 vector potential, what is the 4 vector potential? You can write it as a mu, and it has 4 components. It's a 4 vector. It has 4 components. A0, this is known as the time component, all right, this is known as the time component, and this is known as the space component. All right. You can call this as the time part or the temporal part, and this as the space part or spatial part. Okay. So 4 momentum has 4 components, the time part and the space part. That's all. Okay. And this is equal to, if you take c equal to 1, this is very simple. The time component is just the scalar potential, the usual scalar potential, and the other one is the vector potential. No problem. This is fine. All right. Now you can remember the gauge transformation like this. This is a mu going to a mu plus dou mu lambda. All right. This is known as a gauge transformation. This is known as a gauge transformation. This is the easiest way to remember it. Okay. Gauge transformation. Now, what does it mean in terms of the components? What does it mean in terms of the components? All right. Now, if you are not familiar with this notation, it's really useful to get used to this 4 vector, their scalar products, etc. We'll be doing many problems in a very easy manner using this this 4 vector notation. All right. So, again I will give you dou mu. Dou mu is given by the time component is the derivative, partial derivative with respect to time, and the other space component is minus the gradient. All right, it's not the gradient. You say it's minus the derivative with respect to space. All right, del vector has components dou by dou x, dou by dou y, and dou by dou z. All right. Now you can see that from here you know that the gauge transformation means A0 goes to A0 plus dou phi by dou t. All right, and A vector goes to A vector plus. There's a minus there. So, minus del vector. All right. So, I'm sorry, this is not correct. A0 going to A0 plus, A0 is 5 plus dou lambda by dou t, where lambda is some function of time and the space parts. All right, t and x comma y comma z. All right. So, the transformation. This is known as the gauge transformation. If we use this part, all right, this thing dou mu equal to dou by dou t minus del vector, A0 is given by 5 plus dou lambda by dou t, and A vector is given by A vector minus del vector lambda. All right. Now, what happens to a Lagrangian if you make this transformation? That's the question. Does the Lagrangian remain unchanged? The question is, what happens to a Lagrangian if you make this combined transformation? Right? One transformation is to scalar potential and the other transformation is to the vector potential. This transformation is known as a gauge transformation. It has a very huge importance in physics. All right, gauge transformation. Now, if you do this to the Lagrangian, you will see that Lagrangian actually becomes. You can just make the substitution. In the place of phi, you put phi plus dou lambda by dou t, and in the place of A vector, you put A vector minus del vector lambda. Okay, and then you will see that this becomes, the Lagrangian becomes, if you make this transformation, the Lagrangian becomes, I will write it as L prime, the transformed Lagrangian. All right, you will see that the transformed Lagrangian becomes like this. It's L, the other Lagrangian, minus these things. All right, del vector lambda dot v vector. This is just straightforward substitution. Minus E dou phi by dou t. All right. Now, if you look at this thing, del vector lambda dot v vector, right? We can, if you look at this, the components of this are, these are minus dou lambda by dou x, x dot, plus dou lambda by dou y, y dot, plus dou lambda by dou z, z dot, and minus E dou phi by dou t. There was no problem there. Now, what is this? What is this? This is known as the total derivative of lambda with respect to time. All right. So, these are due to the implicit dependence on time, because x, y and z depends on time. So, you take the derivative of lambda with respect to x, multiply it with the derivative of x with respect to time. So, this is simply L prime is equal to L minus d lambda by dt. Okay. This is the change to the Lagrangian. So, the Lagrangian actually changes under a gauge transformation. Okay. Lagrangian actually changes under the gauge transformation. Okay. So, the option C is also wrong, because it changes according to the gauge transformation. Now, if you are not very clear about this, you can just check what is d lambda by dt. We know that this is a function of x, y, z and t. Okay. So, you know that d lambda by dt is equal to, I will write it here. Okay. You can just check, d lambda by dt is equal to dou lambda by dou x, x dot, plus dou lambda by dou y, y dot, plus dou lambda by dou z, z dot. All right. So, this takes care of the implicit dependence on time, because x, y and z all depend on time, and there is an extra term which takes care of the explicit dependence on time. So, that would be dou lambda by dou t. All right. That is exactly what we have here. Okay. That is exactly what we have got here. Right. This thing. Right. Okay. So, finally, option C, option C is also wrong. So option D is the correct answer. Okay. Under the gauge transform of potentials, L, the Lagrangian, changes by a total time derivative. Total time derivative. And it's easy to see that the equations of motion do not actually change. Right? When the Lagrangian changes by a total derivative of a function, the equations of motion remain unchanged. Okay. I hope that's clear. Now, here is another question which was asked in the part of classical mechanics. Okay. It's asked in the NET JRF June 2011 question. This is a problem from relativity. This is a problem from special relativity. Okay. And there are different ways to solve this. Okay. But I want to introduce to you a very simple way of dealing with such problems that also involves 4 vectors. Okay. So in our classes which will be following, we will actually focus on these easy methods of solving problems because it saves us a lot of time. If you save a few minutes, a couple of minutes on a problem, that is hugely helpful in a competitive exam like this. Right? So for that we will get used to some of the tricks. Right? And here is the question. Consider the decay process. Tau minus gives pi minus plus nu tau. Right? This is nu, it's a neutrino. Right? In the rest frame of tau minus, right? In the rest frame of tau minus. Now we are looking at this whole process in a rest frame of tau minus, which means that in your frame, in the laboratory frame, the tau or the tau particle is at rest. The masses of tau minus, pi minus and nu tau are m tau, m pi and 0. Right? So the mass of the neutrino is taken as 0. Very important. All right? We can use this fact. Mass of the neutrino is taken as 0. The question is, what is the energy of pi minus? You need to find E pi. All right, you need to find E pi. All right, now how do we do this? Right? There are different ways to do this. One way to do this is the traditional way, which is known as you consider the energy conservation equation. You equate the energy on both sides. Okay. And you also use the momentum conservation. Momentum conservation. You use energy conservation and momentum conservation. Okay. And then you can play around with the equations and solve for energy. Right. But we will be doing it in a slightly more easier manner using 4 vectors. Right. So instead of energy conservation and momentum conservation separately, what we will do is we will talk about a 4 momentum conservation. Okay. 4 momentum conservation. We will talk about a 4 momentum conservation. So there is a quantity called 4 momentum. And the time, the 4 momentum, as I said, it has a temporal part and a spatial part. So the temporal part, the time part of a 4 momentum is energy divided by the speed of light, and the space part is the usual 3 vector momentum. Okay. Now I will write it like this. So the 4 momentum conservation, I will write it. So for the 4 momentum, I won't use a vector sign. If I use a vector sign, it means that it's a 3 momentum, usual 3 momentum. All right. So I'll write it like this. P pi, right? P pi is equal to, or P tau, sorry. P tau is equal to P pi plus P nu. This means that the 4 momentum on the left hand side, right, the 4 momentum of the decaying particle is equal to the sum of the 4 momenta of the product particles, all right, the pi and nu. Now we can, it's most convenient, I will tell you why we are doing this. We will write this equation in this form. P tau minus P pi is equal to P nu. Okay. The reason why we are using is that we can make use of this relation. P square is equal to m square c square. P square means P dot P, the scalar product of the 4 momentum with itself, the scalar product of the 4 momentum with itself. Okay. That's the result, it's a non-result, it's equal to m square c square. It's a relativistically invariant quantity. M is known as the rest mass. M is known as the rest mass. Okay. So we can use this result, right? We can use this result. Now using this result, you will see that we will also make use of the fact that P tau is at rest in the frame that we are talking. All right. We said that we are talking about the whole process in a frame, from a frame in which the tau is at rest. Okay. So now you square on both sides. All right. Now you square this on both sides. So you will get P tau minus P pi square. P tau minus P pi whole square is equal to P nu square. all right, p nu square. And what's p nu square? We said that p square is equal to m square c square, and for the neutrino, p square is equal to m square, and neutrino mass is 0. We are taking the neutrino mass as 0. Right? So we immediately get on the right hand side 0. That's very convenient. That is very convenient. Now let's expand this. This is equal to p tau square, usual thing, plus p pi square. Remember that these are scalar products, okay, of vectors. When you say p tau square, it means p tau vector dot p tau vector, and this vector are 4 vectors. Okay? And there is this minus 2 p tau p pi. Okay? That's equal to 0 because this term is 0. Okay? Now we can use the fact that p tau square, right, I'll write here, p tau square is actually m tau square c square, as we just said. Alright, p square is m square c square, 4 momentum square. And p pi square, again, it's equal to m pi square c square. Alright, and there is this extra term here, which is equal to 2 p tau. So I'll write it in the component form first, and then we'll multiply. Right? As I said, a 4 vector has 4 components. One is the time component, and the other are the 3 spatial components. Okay. So what are the components of p tau? I'll just write it like this, so that the time component of a 4 momentum is the energy divided by c. Okay. The spatial part are simply, I'll write it as p tau vector. Okay. So this is the time part, and this is the space part. And here also you will have e pi divided by c, comma p pi vector. All right. So these are the 4 components. All right. These are the 4 components. When I put a vector here, it means that there are 3 components here. It's a notation. Right. We cannot write all the 3 components always. You don't have to do it. Okay. This is a notation. This means that these are 3 components. All right. So this is one time part, and this is the spatial part. Okay. Now this is actually a scalar product between these 2 vectors. Now how do we usually take a scalar product? How do we usually take a scalar product? Okay. We know that for a 3 vector, okay, for a 3 vector, the scalar product is given like this: a vector dot b vector is equal to ax bx, right? Or I'll write it in terms of 1, 2, 3, a1 b1 plus a2 b2 plus a3 b3, right? These are scalar products of 3 vectors. Now what if these are 4 vectors? If there are 4 components, okay, 4 components, then the scalar product goes like this. It is a0 square, right? Or a0, not a0 square, it's a0 b0. You multiply the 0th component minus a vector dot b vector. Okay, there is a relative minus sign here. That's known as the geometry of space-time. Okay, it's because of geometry is Minkowski geometry. So you just have to multiply the components by the corresponding components on the other side, and you will have a minus sign between the time part and the space part. Okay, so that gives us this is equal to m tau square c square plus m pi square c square. All right. Okay, so that's equal to, I write here m tau square c square plus m pi square c square minus, okay, you have got a 2 here, okay, 2 here, and you will have e tau e pi divided by c square. You are multiplying the 0th component, e tau e pi divided by c square, okay, and you multiply the space part also, p tau vector dot p pi vector. Because there is a minus sign here, okay, I will put a bracket here, minus p tau vector dot p pi vector. Okay, all right. This is equal to 0. Right? Now I will write it like this: m tau square c square plus m pi square c square minus, okay, remember that there is a minus sign here. This is the only thing that you need to be worried about. Okay, and what is E tau? What is E tau? We know what's the energy of the tau particle. We know that the particle is at rest. So the total energy is the rest energy. There is no kinetic energy. It is at rest. Alright. So the rest energy in relativity is known as, it's given by m tau c square. Okay, that's known as the rest energy of a particle. Mc square, E is equal to mc square. Okay, E is equal to mc square actually corresponds to the rest energy. If you take the total energy is E is equal to gamma mc square, that would be the total energy. But we are talking only about the rest energy. Right? When V is equal to 0, gamma becomes 1. Okay. All right. So since we know that this is at rest, this becomes 2 m tau c square, and you have got e pi here. Okay, so the e tau is m tau c square, so there is divided by c square minus, what is this? We are again making use of the fact that the tau particle is at rest, which means its free momentum is 0, it's at rest. Okay, the tau particle is at rest. So we are making use of the fact that p tau vector is equal to 0. Right? So by taking this combination, we have easily eliminated p vector pi in this single equation. All right, so this is 0. Okay, this is equal to 0. Now it's only a question of solving for e pi. Okay, we have got m tau, we have got m pi, and we have got 2 m tau c square by c square. All right, so you can cancel these things. Okay, and it's just a matter of solving. This is equal to 0. This means that e pi is equal to, all right, e pi is equal to m tau square plus m pi square, okay, multiplied by c square divided by 2 m tau. Right, you just rearrange these things. This is the answer. Okay. Now I explained the steps really in a detailed manner, but if you get used to this, this is just a 4 steps problem. Right, it may be a 5 marks problem. It's just a 4 steps problem. What we do is that you write the conservation of 4 momentum as such and combine it in such a way that some of the terms, or that the unnecessary momenta gets cancelled off. Okay, so I put it like this, squared it, equated it to 0 because p nu square is 0, and you got the answer. This is a very easy problem. All right, so the answer is option B. Right, answer is option B. I hope that's clear. It's not a very difficult problem if you know how to deal with this for momenta. Okay. All right. So here's the third problem. A double pendulum. This again was asked in the December NET JRF exam in 2011. Right? A double pendulum consists of 2 point masses. Okay, 2 point masses m. These masses are equal, which makes it convenient for us. M attached by strings of length L, as shown in the figure. Right? As shown in the figure. This is the figure. The kinetic energy of the pendulum. What's the kinetic energy of the pendulum? All right. Now the easiest way to do this is to go systematically. Right? Systematically means what's the kinetic energy? Kinetic energy is half m x dot square plus y dot square plus z dot square. Right? Since you have 2 masses, 2 objects, you will have to add the mass of 2 objects. All right. So we can write as x1 dot square, y1 dot square, z1 dot square plus half m x2 dot square plus y2 dot square plus z2 dot square. This is the kinetic energy. All right. Now we need to write this x1 dot, y1 dot, z1 dot, etc. in terms of theta 1 and theta 2, and then square and add. Our job is done. All right. Now how do we do that? So we'll just extend this and say that this is the y-axis. Okay. This we can take it as the x-axis. Right. It's in 2 dimensions. So you just have, in order to find the kinetic energy, is just do half m x dot square plus y dot square. All right. Now let's look at this. Okay. So this length is given as L. Okay. So the coordinates of this mass m, we'll call it as x1 comma y1. All right. The coordinates of this mass m2, we'll call it as x2 comma y2. Okay. This is what we'll do. So what's x1? x1. What's x1? Right. What is? We make use of this x1. What's x1? x1 is actually this length. Am I right? Because this is the x-axis. So this length is known as x1. Right. So from or we can say this is the length. Okay. This length is x1. Okay. So from this trigonometry, you see that x1 is equal to L sine theta 1. Okay. And y1. y1 is equal to L cos theta 1. It's obvious because this length, this is y1, or the y coordinate of this particle of mass m. This is L cos theta 1. Okay. All right. What about the second particle? What about the second particle? We will write it as x2 is equal to, here if you got x2 here. All right. Now x2, if you remember, if you are careful, x2 is this whole length. Okay. This is x2, and what's y2? y2 would be this whole length. Okay. So x2 and y2 are the coordinates, or the Cartesian coordinates of this second mass. Now if you if you are really careful and if you get this, all right, the problem is done. Right? In order to analyze this, you just have to know basic trigonometry. All right. So what we did here is that we said that x1 is this length, okay, y1 is this length, fine. What about mass 2? For mass 2, x2, the x coordinate is this whole length, okay, that is x2. And what's y2? y2 is this whole length, okay. All right. Now we can do it. You see that x2 is equal to, let's write it as L sin theta 2 would be this length, all right, L sin theta 2, that's this length. And what this length we need, we already know that this is L sin theta 1. So x2 is L sin theta 2 plus L sin theta 1, all right. Similarly, you will see that y2 is equal to L cos theta 2 plus L cos theta 1, all right. We need, now it's just a matter of taking the derivatives and squaring them, right. So we see that x1 dot is equal to L cos theta 1 dot, you just take the time derivative, all right. And what's y1 dot? y1 dot is equal to minus L sin theta 1 dot, all right. What's x2 dot? x2 dot is equal to L cos theta 2 dot plus L cos theta 1 dot, all right. y2 dot is equal to L minus L sin theta 2 dot minus L sin theta 1 dot, all right. Now you can find x1 dot square plus y1 dot square. We know that, okay, we know that T is equal to half m, right. Since the mass is the same, we can take it outside, all right. Half m x1 dot square plus y1 dot square plus z1 dot square plus x2 dot square plus y2 dot square plus z2 dot square, all right. So you just square and add these things, you get the result, okay. So let's just calculate this thing first, or we can write it together, okay? There's no problem. So this is equal to half m, right. You just square these things and add, right. You square these things and add. So from here you will have L square cos square theta 1 dot square, okay. And from here, okay, it is plus L square sin square theta 1 dot square, okay. And you just square these things and add, all right. You just square these things and add. And okay, I'll just write it down, okay. You can just square and add using the a plus b whole square formula, plus L square cos square theta 2 dot square plus L square cos square theta 1 dot square, all right. You just square these things, all right. A square plus b square, there's also plus 2ab term, plus 2L square, okay, cos theta 1, wait a second, I'll write it here, plus 2L square cos theta 1 cos theta 2, okay, theta 1 dot theta 2 dot, all right. This term is just the square of this, all right. L square cos theta 2 square plus L square cos square theta 1 dot square plus 2L square cos theta 1 cos theta 2 theta 1 dot theta 2 dot, okay. Plus again you will have these terms L square sin square theta 2 dot square plus L square sin square theta 1 dot square, okay. And here also you will have a plus 2L square, here it is sin theta 1 sin theta 2 theta 1 dot theta 2 dot, okay. So you just add these things. You notice that cos square theta 1 plus sin square theta 1 is 1, so you get an L square theta 1 dot square from here, okay. Here cos square theta 2 plus cos square, you see that here there's a cos square theta 2, here there's a sin square theta 2, that gives you L square theta 2 dot square, okay. And here you also get an L square theta 1 dot square, all right. And finally all these terms will nicely combine, all right. And finally you will get this result, If you combine this properly, you get, see, there is an L square theta 1 dot square from here, and there is another L square theta 1 dot square from these terms. Okay. So that would be twice L square theta 1 dot square. There is this mass also, right? Half m stays here. So that is, there is this twice L square theta 1 dot square, plus there is also this once L square theta 2 dot square. Okay. Now, in order to combine these terms, all right, in order to combine these terms, if you look at these terms, it's cos theta 1 cos theta 2 plus sin theta 1 sin theta 2. All right. Okay. So this is it is just cos. You have got this 2 L square theta 1 dot theta 2 dot, and this would be cos theta 1 minus theta 2. Okay. This is the thing, because cos theta 1 cos theta 2 plus sin theta 1 sin theta 2 is cos theta 1 minus theta 2. Okay. That is the thing. So we have got the answer here. This L square is pulled out here. Okay. So it's half ml square 2 theta 1 dot square theta 2 dot square 2 theta 1 dot theta 2 dot cos theta 1 minus theta 2. So option B is the correct answer. Okay. That's what we obtained. Okay. So this is not very difficult. Okay. Once you know what to do. So the thing is, what we did is that we found x1, y1 in terms of theta 1 and theta 2, x2 and y2 also we found in terms of theta 1 and theta 2. Then it's just a matter of squaring and adding, and we use this trigonometric identity cos theta 1 minus theta 2 is equal to cos theta 1 cos theta 2 minus sin theta 1 sin theta 2. Okay, that's what we have done here. All right. Now, yeah, these kinds of problems are being asked. Right? As I said, this is a question that was asked in one of the previous exams. All right? And if we really study, all right, we'll get familiar with these kinds of problems, and in the exam, such problems may not pose a huge problem. It's not very difficult. Right? Now we'll take a short break for 5 minutes. The link for your ticket for taking part in the competition, the problem solving competition, will appear in the links. In the comment, in the comment. Okay, you can register by going to that link for this competition. Okay, and right. So you can register by going to this link for the competition, and then the question will be sent to you through email. You can solve it, and yeah, then it's easy. All right. You just solve it and send it back and win attractive prizes by Unify. Okay. So with this, a 5 minutes break before we continue into the next session, next problem. Okay. This is the time for you to take part in the competition. All right. To get the ticket to your competition. I wish you all the best. I hope, okay, you all can solve the problem without much difficulty in an original manner and send it to the email. Okay. All right. So we'll restart the problem in exactly 5 minutes. Okay. So the link will be active only for exactly 5 minutes from after it appeared in the comments. Okay, only exactly 5 minutes, and after 5 minutes you won't be able to take part in the competition. Right? So this is the window of opportunity. Okay? This 5 minutes is the window of opportunity for you. You can register, take part in the competition. I wish you all the best. Okay. So your window of time is closing quickly now, a few more seconds. I hope you all have registered for the competition. Let's continue now. Okay, maybe a couple of more seconds and then we will continue. All right, here is the next question. Here is the next question. We are continuing our problem session. Okay, a constant force F is applied. Said it's a constant force. It does not change with time. A constant force F is applied to a relativistic particle of rest mass m. If the particle starts from rest at t equal to 0, its speed after a time t. What's the speed after a time t? Okay. So this is an initial condition given. If the particle starts at rest, okay, it's at rest at t equal to 0, that's the initial condition. Now the question is, which equation have you to solve in order to find this thing? Okay. So what you must remember is that the equation, Newton's second law, F is equal to dp by dt is valid in relativity also. Okay, it's valid in relativity also. Only thing that you have to take care is, now the p vector is not mv, this is Newton, okay, but p vector is equal to gamma mv, alright, p vector is equal to gamma mv. That's a relativistic expression for momentum. So relativistic expression for momentum. And what's gamma? Gamma is simply 1 by square root of 1 minus u square by c square. Right. Now we can just set this equation up because we know the force, we know the equation, we know the expression for momentum. We can just set this equation up and solve it for u, integrate it and solve it for u. That's how we solve this problem. You see that it's an easy problem. Okay. So we use the fact that it's one dimension, so you don't need this vector sign. Dp vector is dp by dt is equal to f. This means that p, okay, you just integrate this, all right. dp is equal to f dt, all right. You integrate on both sides. So p is equal to ft, because f is a constant, plus there is a constant. Okay, p is equal to ft plus constant. Okay, and we can fix this constant by noting that initially when t equal to 0, p has to be equal to 0. Right, you put it here. You put t equal to 0, p equal to 0, then constant has to be equal to 0. So initial condition has helped us to fix the constant of integration, and it's equal to 0. And what do you get? Simply p is equal to ft. Right? We have solved it. We have integrated it. Now what you do is that we know that p is equal to gamma mv or gamma mu. Okay, gamma mu for a relativistic particle. All right. So that is mu by square root of 1 minus u square by c square. That's equal to ft. Okay. Now you just solve. Okay, now we just solve for u. It's not very difficult. You just square and rearrange things, and finally isolate this u. You will get u is equal to f by mt divided by square root of 1 plus ft divided by mc whole square. All right. So this is the answer. This is how you do that. Okay. I will just repeat how we did this. We made use of the fact that dp by dt is equal to f. Okay. This is the information that you need to have in your mind, that even for relativistic particles, Newton's second law is valid. Only thing you have to do is that you should modify the momentum, expression for momentum appropriately. Okay. Now you just put this, you just write this equation of motion, okay. Integrate it for p, you get p equal to ft, right, when you use the initial condition. Right. Now what you do is that you make use of the fact that p is equal to gamma mu. Right. So which means that mu divided by square root of 1 minus u square by c square is equal to ft. Now you just isolate u, you just square on both sides and then take square roots, etc. Isolate this u and you will get this result. Okay. I hope that's clear. Even though it looks slightly difficult problem at first sight, if you know what to do, all right, it's quite a simple problem. Okay. All right. Okay, here is another problem, and these kinds of problem are always asked in your NET JRF exam. All right, every year in every exam there is one question, at least one question, sometimes more than one question, at least one question of this type. All right, it's regarding the phase space trajectory or phase space portrait, phase space trajectory. Okay. So you know that there's phase space is the state space of a classical mechanical system. If we use the Hamilton's equations of motion as the dynamical equation. So that means that every point in your phase space corresponds to just one possible state of the system. All right, and this point is actually evolving. Right, if this is the phase space, you will see that the point in phase space, if this is the state, the momentum and position at. So if you take one point in phase space, it corresponds to all the positions and momenta. Right, all the coordinates of position and momenta. So for a single particle, the phase space is 6-dimensional. Okay. All right. You can talk about a single particle in one dimension, moving in one dimension, and then the phase space is just 2-dimensional. All right. And then you will have this, this is the state at some point, this is the state at some other point, and if you look at all these states, you will see that it traces a curve in phase space. All right. The state actually evolves with time and it traces a curve in phase space because the state changes. All right. This is the initial state, this is the state after some time, this is the state after some time, etc. Right. So these trajectories are known as the phase space trajectories. All right. So it's the phase space, the coordinates are the momentum and the position. So what is the most suitable answer among these? All right. Okay, so let's look at this. The trajectory on the z-pz plane or the phase space trajectory of a ball bouncing perfectly elastically of a hard surface at z equal to 0. Right? So you have got z equal to 0, that's the floor, and your ball is bouncing perfectly elastically from the ground. Right? So this means that z less than 0 is forbidden. Right? The ball does not enter the region of z less than 0. Okay? So that this idea helps us to eliminate a few options. Couple of options. Okay. So if you look at this diagram, it has, this is z equal to 0, it has trajectories in z less than 0, but a bouncing ball, it cannot have trajectories in the region z less than 0 because it reaches z equal to 0 and then goes back. Am I right? So this can be eliminated and this also can be eliminated because there are trajectories in z less than 0. Okay. Now it's either this or this. Now you just look at the physics. Now you just look at the physics. What happens? What happens? Right? The ball comes, it bounces off the ground and then it goes up, and as it goes up, what happens? The momentum decreases, momentum comes to 0, and then the ball comes down, which means that the momentum increases. Right? So what happens is that the ball bounces from the floor, it goes up, and the momentum keeps on decreasing until the momentum becomes 0 at the maximum height, and then the momentum increases in the opposite direction. Right? Okay. So if you look at this, let's take this as the initial state. All right, z equal to 0. At z equal to 0, the ball is bouncing and the momentum is maximum. You see that as z increases here, okay, the momentum is actually decreasing. Okay, the momentum is actually decreasing and it becomes 0. Fine, it's just as we said, right? And then what happens? The momentum increases in the opposite direction. Okay. So this trajectory corresponds, it's a perfectly elastic collision. This corresponds to a particular energy E. If you start with a particular initial energy E, it would be this. If you start with a lower energy for a ball, this would be the trajectory, etc. Right? So this is the correct option. All right. So there are a few tips and tricks in order to solve this phase space trajectory problems. We will be dealing in more detail with it, in more detail about this phase space trajectories in our classes which will follow. Okay. All right, and if you can also look at this, all right, if you have any confusion, you can also look at this image. Okay, what happens here? You see that momentum starts at 0 here, and as z increases, momentum increases. All right, so this diagram corresponds to momentum increasing. All right, you see the momentum is actually increasing, right? Momentum increasing as z increases. Okay. So this is not our situation. So the most suitable answer is this. Right? Now usually it's instructive. All right, I'll give you this tip. It's instructive to put this arrow marks on these trajectories. In the exam, they may put an arrow mark or they may not give an arrow mark. All right. So the arrow mark tells you in which direction it moves in time. All right. In which direction does it evolve. All right? So there's a rule of thumb in order to put this arrow mark. There are 4 quadrants. All right. If the momentum is positive, it's always moving to the right. Right? Am I right? If the momentum is positive, it has to be moving in the positive x direction. So the arrows goes like this. Okay. Arrows are like this. Now, I'll also just tell you that this corresponds to a simple harmonic oscillator, simple harmonic motion. All right, corresponding to simple harmonic motion, you have got ellipses in the phase space. All right, and the arrows will be like that. Okay, arrows will be like that. If the momentum is negative, the arrow is towards the left. So if you are asked the phase space trajectory for a simple pendulum or generally simple harmonic motion, this is the phase space trajectory. All right, and these curves, all right, these correspond to different energies. These correspond to different energies. Now, you can also see this by looking at the expression for the Hamiltonian. Expression is equal to p square by 2, and we will be mostly dealing with one-dimensional system because only that we can draw on a plane, okay, or a sheet of paper. So it's h is equal to p square by 2m plus v. All right. Now we are saying that this Hamiltonian is conserved quantity, so you'll have p square by 2m plus v is equal to e. All right. Okay. So this equation for conservation of energy, where the equation for the total energy is the curve traced by the it represents the curve traced by the what do you say, the representative point, right, or the point in phase space by the state in phase space. So this is the equation, and you can easily see that this gives an equation of an ellipse. This gives equations for ellipses in the case of simple harmonic motion. It's not very difficult to see. Here is another question again asked in the same examination. All right, so there were two questions from this session. A bob of simple pendulum which undergoes small oscillations is immersed in water. It's immersed in water, which means that it's damped. Its amplitude decreases as it oscillates. As the simple pendulum oscillates, its amplitude decreases. Which of the following figures best represents the phase space diagram for the pendulum? Right. So I already said that this is the phase space diagram of a pendulum. All right. Not always, if it's not if there is no damping, because if it starts at a particular energy, it continues along the surface of the same energy. All right. So in the case of two-dimensional phase space, that constant energy surface is a line. That's why we get the trajectory just from this equation. All right. We get the trajectory for one-dimensional system. We get the trajectory. All right. The conservation of energy. Conservation of energy directly gives you the trajectory. All right. So remember this, for a one-dimensional system, the conservation of energy directly gives you the trajectory of the particle in phase space, or it gives you directly the phase space portrait. Why? Because the constant energy surface is a line. Right. Constant energy surface is a line, and the trajectory is also a line, and the particle, if it has a constant energy, it cannot escape this line because the energy does not change. All right. But what happens if there is damping? That means it loses energy to the surroundings. It loses energy to water. Then what happens? It starts here, but it loses energy slightly, and it goes to lower and lower energy, and then it goes towards rest. All right. It approaches towards rest. All right. That's what's happening here. So it's not this. It's not this. It has to be either this or this. All right. We know that it has to be this because if you put the arrow marks, all right, the arrow mark is towards the right when the momentum is positive, it's towards the left when the momentum is negative. So this is the direction, right? This is how it goes. So this exactly corresponds to what we need. Okay. So you see that it starts at a higher energy, it loses energy, and it goes to an inner surface, it goes to a surface or a line of a lower energy, and finally it approaches towards the equilibrium point. It approaches the equilibrium point. Okay. What is this? Okay, this may be confusing. It looks almost similar, right? What is this? If you put the arrow marks, you see that this is some kind of pendulum which increases energy. So if you are pumping it, if you are giving energy, if you are giving an external energy to this pendulum, its amplitude increases, or the energy keeps on increasing, and it goes to higher and higher energy surfaces. All right, that's what's happening. So this is known as a forced oscillator, forced oscillator. You can call it as a forced oscillator. Okay. All right. So here is another problem. Yeah, this is again from special theory of relativity, also asked in December 2011 net. Two events separated by a small distance, 9 × 10⁻⁹ meter. All right. Right? So we can write the distance, spatial separation is delta is equal to 9 into 10 raised to 9 meter, are simultaneous in one inertial frame. So in this frame, it is simultaneous. Right? The events happen exactly at the same time. The time interval between these two events in a frame moving with a constant speed 0.8 c. Alright. So you have got another frame which moves with a constant speed 0.8 c with respect to u. So you got another inertial frame. Okay. Now what's the question? What's the time interval in this new frame? So what do? You just use the Lorentz transformation equations. Okay. So this is an easy problem there. So you have to be familiar with the Lorentz transformation equations, and it's very convenient to remember the Lorentz transformation equations in the differential form. Alright, in the differential form. So if you remember the Lorentz transformation equation, it's simply given x prime is equal to gamma x minus vt. Right. Now, in order to get the differential form, you just put a delta here or d here, all right. Why does it happen? Because we know that Lorentz transformations are linear transformations, all right. So if you just substitute x by delta x, etc., you will get the corresponding differential form. Now this is easy. You write the Lorentz transformation in the differential form, and you have got delta x equal to 9 into 10 raised to 9, delta t is equal to 0. You just substitute. It's just blind substitution, okay. And the velocity is also given, where gamma is equal to 1 by square root of 1 minus u square by c square. The velocity is also given as 0.8 c. So you just substitute, do the calculation, and you will get the answer as 40 seconds. That's the correct answer. Right? So the important thing that we see here is that the events which are simultaneous in one frame. Right? So in one frame, the events have happened at exactly the same time. They are simultaneous. They are not simultaneous in some other frame. Okay? So in other words, simultaneity is not absolute. Right? That's a very important result or consequence of a special theory of relativity. So I'll just do one more problem. This is an easy one, again asked in the same examination. If the Lagrangian of a particle moving in one dimension is given by this is the Lagrangian. All right. What's the Hamiltonian? What's the Hamiltonian? So once you are asked to find the Hamiltonian from the Lagrangian, what you do first is to find the momentum. Since it's one dimension, you don't worry about x, y, z. So P is equal to dou L by dou x dot. Okay. P is equal to dou L by dou x dot, and what is it? Dou L by dou x dot is equal to 2x dot divided by 2x, that's equal to x dot by x. So you've got P is equal to x dot divided by x. Okay. Now you look at this system. So we know that the Hamiltonian is the total energy written in terms of the momentum. Hamiltonian is the total energy written in terms of the momentum if there are a few conditions to be satisfied. All right. What are the conditions? One condition is that the transformation equations, right, the transformation equations should not involve time explicitly. So if you are going from Cartesian to some other coordinate system, the transformation equations should not involve time. In this case, there is no transformation equations. We are talking about one dimension, Cartesian coordinates. So that condition is satisfied. All right. Another thing is that the potential should not depend on velocity. So both these conditions are satisfied here. Okay. So the real way to do this, the correct way to do this is that this method always works. All right. H is equal to summation over I P I Q I dot minus L. This is the Hamiltonian, right? But sometimes you can simply write it as T plus V. All right. So here, if you take this as T minus V, the term quadratic in velocity, you can call it as the kinetic energy. So we can write the energy function H, okay, x dot comma x as x dot square by 2x plus v of x, or you can use this formula, you get the same result. All right. Now if you want the Hamiltonian, okay, you should substitute all x dot by p. All right, all x dot by p. Right. So we already saw that p is equal to dou L by dou x dot, that's equal to x dot divided by x, which means that x dot is equal to px. X dot equal to px. Now we just substitute px here, it becomes p square x square divided by 2x plus v of x. Okay, so it's p square x divided by 2 plus v of x. That's the Hamiltonian here. All right. So it's x p square divided by 2. This is the correct answer. That's the Hamiltonian. Right. So the main mistake that people make is they'll write the Hamiltonian in this form itself. All right. But this form is not allowed because the Hamiltonian should not involve any velocity terms. Right. So in your Hamiltonian, you shouldn't have velocities. You should substitute all velocities in terms of momentum. The Hamiltonian by definition is a function of momentum and position. right? The canonical momentum and the position. Okay. All right. I think with that, time is up for today. I hope to meet you tomorrow again. All right. We'll have one more session on classical mechanics problems, and that will be done tomorrow. Okay. Thank you for attending the lecture. I hope to see you tomorrow.